to our examination of this paper, Space-Time Algebra as a Powerful Tool for Electromagnetism. I'm very much enjoying reading through this paper in great detail, except I'm noticing that it's taking quite a long time. We're working at basically like a full course for each of these sections, and that's running a little less than an hour, but some of them are very close to an hour. So if I roughly said an hour per each of these, already there's 8, 9, 10, 11, 12, 13, 14, 15, 16. There's like 17 hours just in section 3. So if I had planned this out, I probably would have tightened it up to a point where I wouldn't have even done it at all. But lucky for everybody, or lucky for me, I didn't actually plan it out. And ergo, I'm going to persist. And I have the time to finish it. So if you have the time to listen, let's just keep going. So where are we now? We are at complex structure. We have done the pseudoscalar Hodge duality. We've done all of this material. And we are going to do complex structure today. So let's begin. So we left off at this paragraph right here. The duality transformation induced by the pseudoscalar I is equivalent to the Hodge star transformation in differential forms, though arguably simpler to work with. Now, I talked about that last time. There is a lot of differences with the Hodge star transformation in its overall structure in differential forms, of course, having to do with you're actually switching between unrelated, vector spaces that are not part of the same vector space necessarily and things like that. But it is the literal equivalent. But what is important about this is that this I splits the space-time into two halves that are geometric complements of each other. And this is the secret that's going to allow us to introduce something that they call complex structure into this, into our organization of the multivectors of the space-time algebra. Exploiting this duality, we can write any multivector M in an intrinsically complex form where, in the sense of I, meaning that the pseudoscalar I replaces the notion of the imaginary number I, right? That's not what we're talking about. We're going to talk about complexification relative to this pseudoscalar. And this pseudoscalar is going to pair all quantities with their duals. And when you do this, our multivector, which previously was the multivector was, let's see if I write it down, it was alpha plus V plus capital F plus fractor T plus, I guess we went with beta I, right? And what we're going to do is we're going to take all four of it, we're going to take all of this stuff, and we're going to actually compress it into just 3 terms. Now, it's a bookkeeping matter in some sense, right? Because this first term, this piece right here, is actually going to be just the sum of the scalar pieces, meaning the actual scalar piece and the pseudoscalar piece. When I say the scalar pieces, I guess I mean the dimension 1 subspaces. So you take the 2 dimension 1 subspaces, and we're going to talk about their sum, which is actually a dimension 2 subspace. So this piece here and this piece here get combined together into a complex scalar, right? So we're going to call that the complex scalar, and that's going to be defined this way. And that doesn't seem so weird. The part that is a little bit stranger is this other part, the complex vector. So let me rearrange this a little bit. So here we have this complex vector piece is what's interesting, because now Z, which would have been a lowercase Roman letter, which is now going to be representing a complex vector, has a vector part, which is grade 1, and a trivector part, which is grade 3. Now, we don't write it as a literal trivector. We write it as the dual of a vector. So any trivector that's of interest in our analysis, if we have some trivector, T, we have to turn that trivector into a vector, the dual of a vector. And you can always do this. Every trivector, there exists a vector whose dual is that trivector. So the way we write a complex vector is with a regular vector summed with a trivector, but that trivector must be expressed as the dual of a vector, right? And this is complicated a little bit also by the fact that over here, I commutes with beta. The pseudoscalar commutes with all real numbers. But I does not commute with vectors. I anti-commutes with vectors. So these two statements are actually equal, right? Because the pseudoscalar anti-commutes with vectors. So this doesn't act strictly like a regular complex number would, right? This does. This is literally like a complex number from complex analysis. This does not act like a complex number. And so now we can ask the question, well, what are space-time products between complex scalars and complex vectors? But that's not hard, because that's just by linearity going to be the space-time product that looks like this. And then you just blow this up by linearity, and you get the space-time product of a scalar with a vector plus the space-time product of a scalar with a trivector plus the space-time product of a pseudovector with a vector plus the space-time product of a pseudoscalar and a trivector, right? All of these things are we can calculate any one of these things with what we know now. So that's not tough. But it's also true that this does not commute, right? This does not equal z psi. I think they actually talk about that in a moment. So using this duality, we can write every trivector as the dual of a vector, and then we can take the vector and dual trivectors, squeeze them together into a so-called complex vector, and likewise we can squeeze the scalar and pseudoscalars together and create a complex scalar. So they say we illustrate this decomposition in Figure 5. I've already discussed this part, but let's look at Figure 5 and see how their illustration goes. So here's Figure 5, and it says complex structure of the space-time algebra. So the complex blade type, there's bivector blades, there's complex vectors, and complex scalars. So buried in the complex scalar now is the regular scalar and the pseudoscalar, and buried in the complex vector is the regular vector and the trivector, and the bivector remains uncomplexified, so to speak. So the complex structure of the space-time algebra, the complementary Hodge-dual halves of the algebra illustrated in Figure 4 become intrinsically complex pairings by factoring out the pseudoscalar I that satisfies I squared equals minus 1. So the complex scalars and vectors have parts that are independent geometric objects. However, the bivectors are self-dual and irreducibly complex objects that cannot be further decomposed into frame-independent parts. So what's going on here is the complex decomposition includes one I, and this side is basically the side that is not being multiplied by I, and this side is the side being multiplied by I. So that's the complex decomposition of the space. Now notice that although these could be basis vectors, these are not the same basis vectors that we were mentioning before, because there's going to be a sign issue that we kind of went through before. but this is a literal Hodge dual, right? By definition, those two are Hodge dual, those two are Hodge dual, and those two are Hodge dual. And this is dual, this is dual, that's dual, and then 1 and I are dual. So the Hodge dual stuff is completely obvious in this decomposition. And the part that is Z is anything that takes is any factor times 1, like alpha plus beta times I. So this section is a basis for Z. This whole section here is a basis, I'm sorry, wait a minute. They're using Z for the vector space, the complex vector space. So, and then they're using this Greek letter whose name I forgot. That's this complex vector space for scalars. Z is the complex vector space defined by these objects, right? And so where the vector part is made of this, and the trivector part is made of the duals of the vector part. And then the bivectors aren't, they're arguably divided up into a complex part, but what it really is it's the part that includes the timelike piece and the part that does not, that's orthogonal to the timelike piece. So this is a bit of a different kind of decomposition. And we will talk about how this splits up later on. But this complex structure is usually, well, so far it's referring to vector plus trivector and scalar plus pseudoscalar. But what's really nice is using this methodology, you no longer see trivectors written down. You no longer see gamma 1, 2, 3 or gamma 0, 2, 3 or anything like that. All you see are the duals of the trivectors written down. So you've compressed the notation even further, and you've basically gotten rid of the explicit trivector form. And to carry on with the reading, alpha and beta are real scalars, v and w are 4 vectors. As anticipated, the trivector, which is the dual of the vector of a vector w, has been expressed as the orthogonal complement of a vector. That's another way of saying, this here, right? This is the orthogonal complement of gamma 0, the orthogonal complement of gamma 1, the orthogonal complement of gamma 2. And in a 4-dimensional space, the orthogonal complement of a vector is a trivector, is a whole volume, right? In 3-dimensional space, the orthogonal complement of a vector is a plane constructed of 2 vectors that are both independently orthogonal of the vector, right? And if you have 2 vectors, they define a plane, and that plane has an orthogonal vector to it. And so 2 vectors, you can actually identify a vector as being orthogonal to 2 vectors, and you can create this cross product notion. But in 4-dimensional space, 2 vectors define a plane, but any given plane has another plane that it's orthogonal to. So you don't have this possibility of a simple cross product in 4 dimensions, which is the reason for that. We talked about that in a previous lesson. And those are pseudovectors, right? Some care has to be taken with manipulation of complex vectors z, right? That's the vector a plus bi, right? Since I anti-commutes with vectors, as a result, complex scalars and complex vectors only quasi-commute. Well, complex scalars and vectors only quasi-commute. And here you have an example, right? You have a complex scalar, hold on, what the heck letter is that? Okay, I reminded myself. It's zeta. I knew that. Sorry, I was just blanking on it. So zeta times z, where zeta is this complex scalar, times z, well, zeta and alpha commute, so you have alpha zeta plus beta I zeta, but that equals zeta alpha, I guess we're using alpha, minus beta zeta I, because we know that I anti-commutes with zeta. So that's not the same thing as z zeta. So because of that, there's this half of it commutes, but the other half doesn't. So they call it quasi-commute. I don't even know if you I would just say they don't commute, but I guess there's some value in understanding that there's this quasi-commutation, but they don't commute. While complex scalars and bivectors commute normally. So complex scalars and they don't have this problem. If z was a bivector, f, it would commute with I. Because remember, I commutes with anything in the even subspace, which includes the scalars, the bivectors, and the quadrivectors. The scalars, the pseudoscalars, and the bivectors. So, thus, the pseudoscalar I is only algebraically equivalent to the usual notation of the scalar imaginary I when restricted to the even graded subalgebra of complex scalars and bivectors. And that's, of course, because in real complex numbers, the imaginary number I commutes with everything, right? In complex numbers, I commutes well, there isn't much to commute with. But the point is what if we're going to substitute capital I, and we're going to say that it sort of corresponds with I, we have to be very careful to have no vectors floating around. No trivectors floating around, right? Which we now write as vectors, as the orthogonal complement of vectors, which is the dual of a vector. And this still is a pseudovector. That's another way of saying it. If you have any pseudovectors floating around, I does not commute with pseudovectors. All right, so let's go on to section 3.5.1. A bivector, like the electromagnetic field, F. Now, notice they're anticipating that the electromagnetic field will be a bivector. This paper hasn't described why. I mean, we should know, because if we're reading this, we probably know about the differential form of electromagnetism, but understand that ultimately the electromagnetic field will be described by a bivector. So a bivector like the electromagnetic field is an interesting special case for the complex decomposition of a general multivector, since the full bivector basis is already self-dual. That means F is going to be some combination. We've already written this down before. F mu nu times gamma mu nu, right? And this thing here covers all possibilities of gamma mu and nu, but we know that they're all dual to one another from our relationships, right? In other words, from the definition of duality. And in fact, they calculate it all right here. And you see that the dual of gamma 1, 0 is, the dual of the bivector gamma 1, 0 is minus the bivector gamma 2, 3. The dual of gamma 2, 3 is 1, 0. The dual of gamma 2, 0 is gamma 3, 1. So all of the bivectors, their dual is another bivector. So if you're a general bivector, you're constructed out of bivectors and their duals, right? Which is sort of obvious if you're dealing with something that is self-dual. So that's the important part. Sorry, not there. Since the full bivector basis is self-dual, it's an interesting case for the complex decomposition. Yeah, so how do you do a complex decomposition when the basis itself is self-dual, right? So that's what they're kind of asking. So how do you do this? So what are they talking about now? Geometrically, these duality relations express the fact that in 4 dimensions, the orthogonal complement to any plane is another plane, not a normal vector as in 3 dimensions. When we can express these relations more compactly by collecting cyclic permutations and writing this, writing the dual of gamma I 0, where I is 1, 2, or 3, so that's a space-like part wedged with gamma 0, is the Levi-Civita symbol times gamma jk. I don't find this very enlightening. I've never found these definitions that have these Levi-Civita symbols in them as really time savers or anything like that. In this case, it's much easier just to calculate the these things straight up, right? It's not hard. But in principle, yeah, you could figure out, okay, you could work in all the subscripts and get these guys to match this formula. And I don't find these formulas very insightful, but you have to do it if it's possible. You've got to express it this way. But okay, so great. You have these formulas that capture the obvious. Let's see. The self-duality of the bivector basis makes the signature of the general bivector mixed. The signature of the general bivector mixed. Well, that's really interesting. So, first of all, a signature, we've been so far, when did our signature calculations, we came up with the whoppingly interesting +1 or -1. So they're saying it's mixed. So let's figure out exactly what that means. That is, although each basis vector has a well-defined signature, that is, each basis vector of the bivector subspace has a well-defined signature. And then they throw down this little example of gamma I0 multiplied by its reverse is 1 times -1 is -1. But of course, that's not exactly the formula, right? The formula is the signature of gamma I0 is reverse gamma I0 times gamma I0 divided by the absolute value of the reverse of gamma I0 gamma I0, right? So that's going to be gamma 0I times gamma 0I, times gamma, not 0I, times gamma I0 over the magnitude of gamma 0I gamma I0, right? And this top one is going to be, this I times I is going to be -1, and the 0 times 0 is going to be 1. So this top numerator is going to be -1. The denominator is going to be the absolute value of -1, which equals -1. So they've ignored the denominator here, and they've ignored it because, okay, come on, these are unit vectors. We know this is going to be a 1. Fair enough, but understand that the real definition of signature is not just a multivector times its reverse. You've got to divide by this factor. And it just so happens if you're dealing with a unit vector, it's pretty easy. But I just want to point that out. If you're a fully spatial bivector, JK, because remember, these Roman indices are 1, 2, and 3. So these are spatial plane elements. Well, that times its reverse is going to be -1 times -1 divided by 1, and you get 1. So you have a positive signature for the purely spatial parts and a negative signature for the time-like parts, which, if we go back to the figure, don't forget that the planes that have a time-like element to it, the time-like basis vector as part of its plane, meaning a plane that's extending in the time-like direction, right? Those have signature -1, and these guys, the duals of those planes, the duals of these time-like planes are all of the space-like planes, which we no longer really write as space-like planes, right? We write them as the dual of time-like planes to capture this sort of complex structure, and those guys have signatures of +1. Very well. And so now they say, although each basis vector has a well-defined signature, and they give these two examples, a general bivector will be a mixture of these two different signatures. Sure, because a general bivector, being some linear combination of basis vectors that have negative signatures and basis vectors that have positive signatures, what is the signature of a general bivector? So consider the simple mixed bivector gamma 1, 0 plus gamma 2, 3 as an example. All right, before we move on, let's just do this computation ourselves. Actually, they demonstrate it right here in the very next paragraph. So they're calculating FF reverse for gamma 1, 0 plus gamma 3, 2. So for gamma 1, 0 plus gamma 2, 3. So the reversal is gamma 0, 1 plus gamma 3, 2. Then you blow this up by linearity to get this structure here. Now what's interesting is when you get this structure, you're going to find that you're going to get pieces that multiply all the way down to a real number. And this is pretty obvious. This is going to be gamma 1 squared times gamma 0 squared, which is going to be -1, right? Oh, well, that's what you see right here. Then you're going to get a part that is a quadravector. But notice how they designed the beginning. They designed F to be completely orthogonal. Gamma 1, 0 is completely orthogonal to gamma 2, 3. In other words, you don't have a gamma, say, a gamma 1, 2 in there, which would blend together with gamma 0, 1 to give you something more like gamma 1, 2 times gamma 0, 1, say, right? In which case you would end up with a bivector, right? Because the gamma 1 parts would go away, and you would end up with a gamma 0, 2 piece. Now, to be clear, if you did have that, if you did have a piece in here that was not orthogonal to one of these two factors, all of these bivectors would end up canceling out, interestingly enough. Maybe we can demonstrate that later. So the result is that this structure for a bivector F, a general bivector F, is always going to end up with just pseudoscalars and scalars. So, which is why we can use this example to be fully general. So when you continue to multiply this out, you get gamma 0, 1, 2, 3, gamma 3, 2, 0, 1, and when you can determine quickly that gamma 3, 2, 0, 1 is the same as gamma 0, 1, 2, 3, which is just I plus I. And then, in this case, this final part, gamma 3, 2 times gamma 2, 3, this becomes -1 times -1, which is +1, right? Which cancels with that -1. So the real parts actually cancel, and you're left with a purely imaginary part for this particular bivector, but the bivector gamma 1, 0, gamma 2, 3. So, okay, so you end up with a pseudoscalar result. But take note that you could have ended up, and you more likely would have ended up with a mixed result, right? If this number here, if gamma 2, 3 was, say, 2 times gamma 2, 3, right? Imagine that. Well, then you would have a 2 here, right? And you would have a 4 here, and you would have there would be a 2 here, right? So there'd be a 2 there. So this would end up being 2 here and 2 here with the 2 here and the 2 here. So that would be a 4. This would still be a -1, but this would be there'd be 4 there. This would be a 4, and you would end up with 3 plus 4i, right? Yeah, I think that's right. 3 plus 4. So a general bivector reversion product, or the reversion square of a bivector, can end up with this, what we're now going to call a complex number, zeta, right? And or it could be purely imaginary, which is in our language purely pseudoscalar, or purely scalar. Now, the rest of this section talks about how you can take this final result of the reversion square and put it into a polar form, a complex polar form. So, for example, 3 plus 4i, if I was to just naturally, left to my own devices, to put it in a complex polar form, I would take the magnitude of it, which is the square root of 3 squared plus 4 squared, and I would multiply it by a phase angle, which would be the inverse tangent of 4 over 3, right? And this number here in complex analysis is completely equivalent to this. And we understand, how do I raise, I need an I there, right? A pseudoscalar I. Now, here we are using E raised to basically a real number times the pseudoscalar I. But we're comfortable treating that exactly like the imaginary complex number. it's a different object for sure than the basic imaginary complex number, but it is still true that they both square to -1. And that's what's critical about the Taylor expansion of this thing. So the Taylor expansion of this thing will work out exactly the same way as it would with a complex number. And so this is always going to be cosine beta plus pseudoscalar basis vector sine beta, right? And we can always use this equivalently just like we would in complex analysis. And we're going to do this a lot because we're going to do this with, and we're also going to do this with hyperbolic numbers, meaning where I squares not to -1, but I squares to 1. So that's the next step. That's what this next set of paragraphs does. But what I'm going to do is I'm actually going to go off menu, and we're going to do this analysis instead of from this paper. We're going to do it from a paper written by Hestenes himself, because I think it's a little bit more comprehensive. Here, it's stated in terms, this paper says, hey, we can obviously proceed this way, and we can, right? It's true. You just think of this in terms of magnitudes and phase shifts, and you can do all of this. They do throw in a factor of 1/2 here that I don't fully understand, and it does not show up in Hestenes's paper in the same way. There is a factor of 1/2 in Hestenes's paper, but it's not put into this phase angle. So I kind of want to figure out what that's all about. So we're going to go off script and study this important concept of creating a canonical form for an arbitrary bivector f, right? We create this canonical form where any bivector f can be turned into a canonical bivector multiplied by a phase factor. And we're going to do that from a different paper, and then we'll come back to this paper. Okay, so I'll see you next time.